All right, guys, welcome to Discrete Math. All right, so this is the last lesson. Oh, giddy up. All right, so this is 8.9, which is called Markov chains. All right, so Markov chains are used to math models that involves finite number of events and events that change over time. All right, so what happens with that? So, well, let's do an example of West Lincoln High School cafeteria food. Okay, so how much do they how do they know how much to fix each day? Well, on Monday they have a certain percentage from each class. So whenever we take attendance, we give it to them. And then just based on historical information, they know how many people are going to eat. Okay, just a standard probability. Okay, so and it's really a Markov chain is used to figure it out. So for example, on Monday they know that 75% of the people eat in the cafeteria. Okay, so they also know from previous surveys or stuff that people, and these are called conditional probabilities. Okay, the probability of that they eat in the cafeteria, given that they ate in the cafeteria, is about 70%. So like if they know that they ate in the cafeteria yesterday, then the chances are 70% of them will eat again today. So same thing, if people didn't eat in the cafeteria, then they're going to eat in the cafeteria. It's going to be about 30%. Okay. Yada yada yada. So like the last one is, well, they know if they didn't eat in the cafeteria that they're not going to eat in the cafeteria the next day. All right. So anyway, you have these probabilities that come down. All right. So this is easy to see in a tree diagram. All right. So for instance, so this is on Monday. So they know that they think that 75% of people are going to eat in the cafeteria and 25 will eat, something else like brought from home, or they choose not to eat. But then going down, like based on those who ate in the cafeteria, then these will 70% of them will and 30% won't. Okay, and those who did not eat yesterday, 40% will eat in the cafeteria, 60% won't. So now the interesting thing is if you notice this on Monday, it adds up to 100%. Okay, on Tuesday, those who ate in the cafeteria, okay, that's got to add up to 100%. And those who did not eat in the cafeteria, the probabilities for that also add up to 100%. Now, the thing about this is whenever you're doing this, you end up multiplying as you go down the path. Okay, so that's what these multiplying. So these are and statements, like the probability that they ate in the cafeteria on Monday and they ate in the cafeteria on Tuesday is going to be, you just multiply those two probabilities. Okay, so you get 0.525. Now the interesting thing is that these four probabilities right here actually do end up adding up to 100%. Okay, so there's a lot of similarities that are going on here. All right, so we can actually put this in a matrix. Okay, so there's three types of matrices, or two types of matrices that we're going to be talking about, and this is very similar to what we did yesterday with Leslie matrix. Okay, we have what's called an initial distribution, we have a transition matrix, okay, and then a transition digraph. All right, so what is this? Well, the initial distribution is 0.75 if they eat in the cafeteria, okay, 0.25 if they don't eat in the cafeteria, okay. And the transition matrix is that as you go across in the rows, it's the 100%. Okay, so we have the 0.7 and 0.3, the 0.4 and the 0.6. Okay, based on that. All right. So now, what do we do? Well, to figure out Tuesday, all we have to do is put this in your matrices and do exactly what we did yesterday. Okay, with the Leslie matrix, and just multiply it out, and you'll figure out the probability that they will eat there. Okay, so it's that they will eat in the cafeteria regardless of whether they ate or didn't eat. So anyway, we can put this in our matrix like what we did yesterday. So let me go ahead and I'm going to get out of it. Okay, and I'm going to go over here and I'm going to open up, and I'm just going to put matrix multiplication calculator. All right. So I'm going to pull up. I think I use this one, the matrix calc. All right. So I'm going to go ahead and click on that. I'm just going to pull up some stuff. Now I'm going to make it a small one. So I'm going to make it a little bit smaller than what we had yesterday. Okay. So on this one, I just got the the 0.75, okay, 0.25. And remember, this one is going to be the cafeteria, so I want the point, I think it's 0.7 and 0.3, okay, that they're going to eat there. And then what's the probability that they don't eat there? Well, it's going to be the 0.4 and the 0.6. Okay. So now what all down here I'm going to do is I'm going to do A times B. Now, A times B. All right. So now if I do that, now I do want the decimals. Okay, I'm just going to hit equals. All right, so if you notice, I just got to do 2 decimal places. I'll try 3. We'll do it again. So let me clear it and hit it. Yeah, so now I exactly match what I have there. So now this is what's going to show up on Tuesday. Right? What if I raise it to a second power? Okay, then what I would end up doing is this would be Wednesday's number. If I had it to the third power, it'd be so Tuesday, Wednesday, Thursday. Thursday is going to be the third power. So this is going to what's happening on the third day. And then if I did it to the fourth power, that's what should happen on Friday. Okay. So the 0.573 and 0.4. So 57% of students will eat on Friday. 43% of students will not eat in the cafeteria on Friday. All right. So let me go back and let's see. So let's see here. So probably don't eat in the cafeteria on Friday. 0.572. So 0.573. That's what we have. Okay, 0.573. All right. And then 427, and it really does. So if you raise it to the fourth power, then it's 4 days later. All right. So so big thing is that initial matrix is going to be a row, okay, must equal 1, and then transition matrix, those rows have to equal 1, right? If you have a stable state vector, that means that the Markov chain are used and converged to a single vector. Okay, that means that eventually they'll stabilize out, and you'll get the same number repeated over and over and over. And that's what happens when it's called a stable, steady state or Markov chain. All right, so who came up with this crazy stuff? All right, well, it was A.A. Markov. He was Russian. Okay, that's why this is the letters of his name in Russian. Anyway, he was a Russian math guy. He was a professor at St. Petersburg. And he won the gold medal in differential equations. Differential equations, that was my favorite class at NC State. It's the class after calculus. So you have calculus 1, 2, and 3, and then you have differential equations. And differential equations is used a lot in engineering. Anyway, this Markov chain theory led to the modern state of stochastic processes. And it's really like a steady state in engineering. It's used a lot, a whole lot. So anyway, that's a little bit of introduction about Markov chains. So I will say this, you do have a couple practice now, so I'd say do your best. Just try those. I do have selected answers, so you can make sure you know what you're doing. And this is the last one, so giddy up. I'm just so excited and proud of you, so do your best, all right? Finish off on a good note. All right, thank you very much.